So let's take a look at several examples of how we can divide the space on which we want to solve the differential equation into small finite volumes. And as you can imagine, the only criterion we have is that all these volumes, first of all, they don't overlap. 2, they fill the entire space. There is no gap in between, right? So any kind of partition of unity is going to work for us. So this type of grid is called a block structured grid. And what you can see is that every piece of grid is logically a rectangle, right? So here, for example, you can separate a rectangle, use this, separate a rectangle over here, and on the grid, on this rectangle, the grid can be arranged into I goes from 0 to Ni, and J goes from 0 to Nj. And this is another rectangle you can draw, right? And so basically we have a partition of unity by first dividing the space. In this case, it's a turbomachinery cascade. We have an array of status upstream and an array of compressor rotors which moves in space, and after which another array of status. And we divide the entire computational space into rectangles and generate a mesh on each rectangle. So every one of these mesh is a finite volume. And every mesh in this case has exactly 4 neighbors, right? It shares a non-trivial interface with 4 neighboring grid points. Okay, so basically for every mesh, we're going to find the 4 neighbors and use the cell averages on that cell and its 4 neighbors to compute the flux on the 4 faces. And then the summation of the flux on the 4 interfaces multiplied by its interface face normal times the interface size is going to give us the time derivative of that cell average, right? Another type of mesh is unstructured mesh. Right, this mesh is a triangular unstructured mesh, and in real applications, unstructured mesh can have triangles. It can have mixed elements also. So in this case, every volume is one of these triangles in 2 dimensions. And in 3 dimensions, these can be tetrahedrals having 4 faces. And these triangles have 3 faces, and every triangle have how many neighbors? It has exactly 3 neighbors, right? So, and each tetrahedral would have 4 neighbors. So these are, for example, the black triangle has neighbors, this one, and this one only. All the others are not going to be counted as neighbors in the finite volume sense, right? If you do other, for example, if you do finite element, maybe these are also going to be counted also as neighbors, but in finite volume, only the cells that shares a non-trivial interface is going to be neighbors. Again, we are going to use this cell and its 3 neighbors to compute the flux across these 3 sides. Okay, and the summation of the flux times the face normal and times the length of the face summed together divided by the volume of the area of the triangle, we are going to get the time derivative of that cell. Okay, so these are the 2 cases where the number of neighbors are fixed. There are also cases where the number of neighbors are not fixed. That also can work. So this is particularly useful for cases where you need very different resolutions in different regions of the space. For example, this is an application in which obviously we want to have very high resolution almost near a contour, and away from the contour we don't need much resolution. So this is the case we can have this kind of hierarchical adaptive mesh refinement like AMR. So there are very coarse grids, and you can have a lot finer grids in where you want to have higher resolutions. And for example, in this volume, the cells, the neighbors which you count as your cells would be this one, this one, this one, this one, this one, and these two, right? So you have 1, 2, 3, 4, 5, 6, 7 neighbors.